In this video, I'm going to explain the second part of the chapter of vectors, which is chapter 8. So the second part is about addition of vectors. To add vectors, we have two rules. We have Chase's rule and the parallelogram rule. First, we will start with Chase's rule. To add two vectors, u and v, first, what we do is we take one of them and we translate it in such a way that the ending point of the first vector, which is this, so the extremity of the first vector, is at the same time the origin or the initial point of the second vector. So the ending point of the first is the starting point of the second. So I'll move vector v, for example. I can move either u or v. I'll move v in such a way that the starting point of v is at the ending point of u. So now we have u, v. So these are two consecutive vectors because one after the other. Now, to construct the sum of u and v, we simply join the 2 points. The starting point will be, the starting point of u plus v will be the starting point of u, and the ending point of u plus v will be the ending point of v. So I'll take this vector, the starting point should be here, and the ending point should be here. This vector in blue here is the resulting vector u plus v. So this is u plus v. Now, here I constructed u plus v by translating v in such a way that the ending point of u is the starting point of v. We could have translated u in the same way. So we got the vector u plus v. Now, this is the first case where u and v are vectors that do not have the same direction. So they have different direction. They do not lie on lines that are parallel or confounded. Now let's consider this case, the second case, where the vectors have the same direction. So if the vectors have the same direction, we have two cases. Either the vectors, like u and v here, are having the same sense or opposite sense. Okay? So if the two vectors have the same sense, as we did before, so I want to move v or u, let's move u for example, in such a way that the ending point of the first, so the ending point of u is the starting point of v. So I'll move them in this way. So we have u plus v. So u plus v starts at the starting point of u and ends at the ending point of v. So this is the resulting vector. Just move it like this. Okay. So this is the resulting vector in green. So this vector is u plus v. Now, what if the vectors have opposite senses? So they have the same direction but opposite senses. So we can take one of them, move it in such a way that the ending point of the first, which is this, is the starting point of the second, which is this. Okay, so the ending point of u is this, the starting point of v. So I put them in such a way. So the resulting vector will be a vector such that it starts at the starting point of u and ends at the ending point of v, which is this. So I will draw this vector in a different color. So this is the resulting vector. Okay. So the vector in pink is u plus v. So this is the case where they have opposite senses. Notice, concerning the magnitude of the vector u plus v, notice that in the case where the two vectors have the same direction and same sense here, what do we have? We have that the magnitude of u plus v, which is the distance from here to here, is equal to the magnitude of u plus the magnitude of v. And notice that in the case where the two vectors have the same direction but opposite senses, the magnitude of u plus v is equal to the magnitude of v minus the magnitude of u. The magnitude of the taller vector minus the magnitude of the smaller one, which are in this case is u minus v. And this is summarized here. Okay, so we notice two things. In case the two vectors have the same direction and sense, we will have this. In case they have opposite senses, we have this. Many students do the following mistake. They consider that u plus v in magnitude, the magnitude of vector u plus v, is equal to the magnitude of u plus the magnitude of v. This is wrong. It's not always true. We've just seen now that it's true in the case when u and v have the same direction and same sense, but it's not true in the second case. Now, what about the case where the two vectors do not have the same direction, which is the first one? So what about this case? I will discuss it here. So, when the two vectors do not have the same direction, we said we find the sum by translating one of them in such a way that the end point of the first is the starting point of the second. So we get u plus v. Notice that this is a triangle, and you know from grade 9 the triangle inequality, which states that in any triangle, the length of any side is less than the sum of the lengths of the other two sides and greater than their difference. So in this case, AC is less than AB plus BC and greater than AB minus BC, or BC minus AB. So AB minus BC or BC minus AB. Now, what's AC? AC is the length of segment AC, which is the same as the norm of u plus v. So I can replace AC by the norm of u plus v. And AB is the norm of u, BC is the norm of v. Similarly here, AB is the norm of u and BC is the norm of v. Now, notice that in the previous slide here, we saw that the norm of u plus v can be equal to the norm of u plus the norm of v in the case where they are collinear with the same direction. In the case they have the same direction and same sense, and can be equal to the difference in case they have the same direction but opposite senses. So we can generalize this inequality here by adding or equal, because they can be equal to the difference and this can be equal to the sum. Now, as for this inequality is simply is another form of this one. Notice it's the same, but we have, instead of plus here, we have minus. And it's easy to deduce this formula from the first one. Simply, you can replace here plus by minus. I mean plus v by minus v. So replace the vector v by minus v. So if we replace v by minus v, we will get in the middle u minus v. Here, we will get the norm of minus v. But we know that the norm of minus v is equal to the norm of v, because opposite vectors have the same magnitude or the same norm. So we will get this. And here also, if we replace v by minus v, we get the norm of minus v, which is the same as the norm of v. The second way of adding vectors is using the parallelogram rule. We can use the parallelogram rule to add vectors that do not have the same direction. So consider here the two vectors u and v, same vectors that we had before, and now we are going to find the sum in a different way. The first way was by translating one of the vectors in such a way that the ending point or the extremity of the first is the origin of the second. Now we are going to do something different. We are going to take one of them and translate it in such a way that the origin of the first is confounded with the origin of the second. So I will do the following. Okay, so now we have u and v starting from the same origin. Now, how do you continue to draw the sum of u and v? So the idea here is to complete this shape to form a parallelogram. So I will complete this shape to form a parallelogram. So I will draw a segment here parallel and equal to this one, to V, and another one parallel and equal in length to U. Okay, now we got a parallelogram, and I will draw the vector, resultant vector, which is U plus V. So we will get U plus V as follows. So the starting point is this, and the ending point is this, which is the fourth vertex of the parallelogram that we formed here. Of course, here the drawing is not very accurate, but the idea is clear. So we translate vector V or vector U in such a way that the two vectors start at the same point, and then we complete the figure to get a parallelogram. We join the origin with the fourth vertex of the parallelogram to get this pink vector, which is here. So this vector is U plus V. Okay, this is shown here also in this figure. And notice that if we call these points A, B, C, and D, let's say this is A, B, so U is A, B, and V is A, C. I'm using the same notation here. So D would be the fourth vertex of the parallelogram A, B, D, C. Pay attention, we read it in a circular form. So A, B, D, C. I cannot read this as A, B, C, D. It's wrong. So either A, B, D, C, or C, D, B, A, or A, C, D, B, and so on. Okay, so if we have this, notice that we have AB plus AC as vectors. So U plus V, which is the same as AB plus AC, is equal to what? To AD. So U plus V is equal to the vector U plus V, which is AD, where D is the fourth vertex of the parallelogram AB DC. Now, if we have ABDC given to be a parallelogram, so I will call this. So as we said, we have to name the parallelogram in order, so in a circular form. So let's start, for example, if this is A, start here with A, then this is B, A, B, D, then C. If we have this a parallelogram, then we can say that AB vector, so AB vector, so this vector, plus AC vector is equal to AD, so AB plus AC is equal to AD, where D is the fourth vertex of the parallelogram. Conversely, if we have AB plus AC equal AD, then we conclude that ABDC is a parallelogram. Now let's look at these two remarks. Here we have, if AB equal to AC, then B and C are confounded points. So this is obvious. Let's say this vector is AB, and suppose that we have the vector AC such that AB equal AC. Since they start from the same point, I cannot draw C in any other way except being confounded with point B. Okay? So C has to be confounded with B for AB to be equal to AC. Now let's consider the second remark. If we have AB equal BC, so let's say this is AB vector equal to BC vector, then notice that ABC have to be collinear points. So we cannot have BC here, for example, because B is the same point. So if I have AB is the same vector, I cannot have BC here because B is the same point. So ABC have to be collinear. So this is the first point. Second, B is the midpoint of AC, and this is obvious. Since AB equal BC, then they are equal in length, and the points are collinear, then of course B is the midpoint of AC. And because of this, we have vector AC equal to 2 times vector AB, and also it is 2 times vector BC. We are going to talk about some properties of vectors. So if you have 3 vectors, U, V, and W, the first property says that u plus v is equal to v plus u. Now we can see this clearly if we draw the sum u plus v using, for example, the parallelogram rule. We complete this to form a parallelogram, and we join the origin with the fourth vertex of the parallelogram. We get the following vector. So this resulting vector is vector u plus v. But similarly, we can consider it to be the vector v plus u, because to find v plus u, we should do the same method. So we translate one of the vectors so that they start from the same origin, complete to get a parallelogram, and so on. So u plus v is clearly equal to v plus u. Now the second property. The second property is the associative property. It says that u plus v between parentheses plus w is equal to u plus v plus w between parentheses. This means it doesn't matter if we start with u plus v first and then add w, or we do v plus w first and then add v. So let's see this clearly. So let's start with the left hand side. So let's do u plus v first. So I will draw the sum of u plus v. Now notice here I drew u, v, and w in consecutive ways. So I'm applying the first rule. The end point of the first is the starting point of the second. So the resulting vector will be, for example, for u plus v, it will start at the beginning of u and end at this, at the end of v. Okay, so this is u plus v. So I did u plus v first, and now I'm adding to the green vector u plus v w. So the resulting vector will be this. So this is u plus v plus w. Now if we start with v plus w first, so I will draw the vector v plus w dotted with a different color. So v plus w will be this. So this is v plus w, and then I add to it the vector u. So I do u plus v plus w. So this pink vector u plus v plus w. Notice that the resultant vector will be the same blue vector. So this is the same as doing v plus w first and then adding to it u. The third property, which is this one, u plus the zero vector is simply u. And the last one, u minus u is equal to the zero vector. By writing u minus u, we mean u plus minus u. So, and this is also obvious because suppose that we have any vector u. Okay, and if we want to take the vector minus u and add it to it, minus u would be the same but in the opposite sense. So minus u would be something like this. And to draw the sum, we know that we should put one way is to put the extremity of the first at the origin of the second. So I will take another vector equal to minus u, and I will move it in such a way that the extremity of the first is the starting point of the second. Notice that going forward, then going backward, we arrived back at the same point. So as if we didn't move at all. So this means we got the zero vector. Remember from the previous video, AA is equal to the zero vector. The fourth point is subtraction of vectors. So subtraction of vectors is similar to addition of vectors because you're just applying the opposite operation. So you're simply adding the opposite vector. So to do u minus v, it's the same as doing u plus minus v. And we already talked about the sum of vectors, so it's exactly the same. What you can do here is the following. So we have u and we have v. So we take the vector minus v. Minus v is the same vector but in the opposite sense, so same direction, same magnitude, but opposite sense. And for example, we apply the first rule, which is drawing them in such a way that the extremity of the first is the origin of the second. So here we move this vector, which is in blue, which is minus v, translated so that the starting point of minus v is the same as the ending point of u. So we got this. Okay, and then we add the mu plus minus v using Chase's relation is this vector. Okay, so u plus minus v is this vector, which is u minus v. So we can see that if I call these points a, b, and c, we can see that ab plus bc is equal to ac, which is the same as saying ac minus ab. So if you take this to the other side, ac minus ab equal to b. So this is another way of memorizing Chase's rule, but in order to reduce the need to memorize, you can always say that, for example, we have here BC. Okay, I can always insert here letter A. By Chase's relation, I can have this BA plus BC plus AC, sorry, plus AC. And we know that BA is the same as minus AB. So this is minus AB plus AC, which is the same as AC minus AB. Some people like to memorize it as a second form of Chase's rule. So saying BC, if you insert A, you get AC minus AB. But I don't prefer memorizations, just memorize one form of Chase's rule, which is the addition form, and you can conclude the subtraction from the addition. Now this is just a remark, a generalization about what I said before. So I said some people like to think about it this way. You insert letter A, so you get AM minus AB. But if you don't want to memorize, which is the better way, as I did before, we can insert here letter A. So this means that this becomes BA plus AM by Chase's relation. And BA is minus AB, so I can write this as AM minus AB. Okay, so you can conclude it in one step instead of memorizing. Now, in this figure, we are given U and V, so this is just a summary of what's U plus V on the figure and what's U minus V using the parallelogram rule. So if we use a parallelogram rule for U plus V, we know that U plus V is this vector where D is the fourth vertex of the parallelogram, so this is U plus V, and U minus V, because minus V is the vector in the opposite sense, so it's this, so U minus V, or minus V plus U will be this vector. Okay, so you can see it on the figure. The last point in this video is about decomposition of a vector. So to decompose a vector into the sum of two vectors, we have two ways, depending on what we are given and depending on what we want. So for example, let's say we have a vector AC and we have any point B in the plane as such. So we're given a vector AC, given any point B in the plane. I can decompose the vector AC into the sum of the two vectors AB and BC as follows. So if I take the vector AB, okay, plus the vector BC, using Chase's rule, AB plus BC is equal to AC. So I'm able to decompose AC as the sum of the two vectors AB and BC, where B is any point outside or any point in the plane. The second way should be related to the parallelogram rule. So the second case is as follows. We are given a vector AC. Okay, so this is vector AC, the blue one. And we are given two lines, intersecting lines D and D prime, that are intersecting at point A. And we want to decompose the vector AC into two vectors whose directions are D and D prime. So the direction of the first vector is D, and the direction of the second vector is D prime. In other words, speaking like not accurately, but just to explain it, it means that the two vectors, one of them has to be parallel to D and the other one has to be parallel to D prime. So to do this, we start from point C and we draw a line parallel to D prime. And we do the same thing. We draw from C a line parallel to D. And we name these 2 points of intersection. This is, let's call it B, and this is D. Notice that ABCD is a parallelogram. So I can say that AB plus AD is equal to AC by the parallelogram rule. Okay?